Hello, everybody, and welcome to this new episode of the Artemis Learning Series. My name is Miriana Somenzi, and I am a researcher in the Ariadne Research Infrastructure. Together with my colleagues in Artemis, I am part of the data infrastructure team, and the focus of my research is artificial intelligence and network science, in particular the field of NLP, so natural language processing. Today, we are going to talk about how we are designing an efficient backbone for the reactive heritage digital twin in the Artemis project, combining network science and artificial intelligence. But first, let me take a step back and start from the beginning of it all, data. So cultural heritage data today is vast, diverse, and often unstructured. It includes text, papers, and reports, which can often be old or heterogeneous, or in different languages and formats, images of building and artifacts, pictures, reproductions, scientific analysis, such as spectroscopy and XRF, and tables, PDFs, CSV, notes from various specialists. So, as a result, we face what we call an information chaos, rich data, but fragmented and disconnected between each other. What do we mean by unstructured data? So it is not that the data that we have has no meaning, it is quite the opposite. Take, for example, these three images in the slide. The first one is a scientific paper about a monument, the Church of Notre Dame. The second one is a picture of a monument, the same monument. And the third one is an AI-generated image of some sort of 3D reconstruction or prediction about that image. As humans, we can easily understand that these three images are connected and they belong to the same monument. For humans, we can use context, prior knowledge, and visual cues to make this connection. For a machine, these three types of representation are just different. There are no links between them. So the machine doesn't see one monument, it sees just disconnected pieces of information. This is what makes the data unstructured. The relationships are there, but they are not formally defined. So the question becomes, how do we make these relationships explicit? How do we move from data that humans can understand to data that machine can also understand and interpret and connect? In other words, how do we turn data into knowledge? Once the raw unstructured data is collected, it needs to be transformed into structured data to provide an efficient backbone for our heritage digital twins. This can be done through knowledge graphs. But what are exactly knowledge graphs? So, behind every complex system, there is a network that defines how its components interact. In the context of cultural heritage, a complex system is not just a collection of isolated objects, but a network of interconnected elements, such as artworks, artists, places, historical periods, materials. The overall understanding of the system does not come from each element individually, but from the relationship between them. For example, knowing an artwork in isolation gives limited information, but connecting it to its creator, its historical context, its location, its related works provides a much richer understanding. In fact, this is what culture is. Not isolated elements, but a network of interconnected informations and meanings. And this is what we call in computer science emergence. So the meaning arises from the interaction between elements and not just from the elements themselves. So, as I was saying, behind a complex system, there is a network. A knowledge graph is exactly that, a network made of nodes which represent things like objects, people, places, or concepts, and edges, so connection, links that represent the relationships between them. From a computational perspective, A knowledge graph is also a mathematical object, where nodes and edges are formally defined and can be queried, so interrogated, analyzed, and reasoned over. Knowledge graphs supported by ontologies, which are the vocabulary that my colleagues previously already explained in this learning series, preserve context, relationship, and meanings, all crucial for cultural heritage. They enable features like multilingual representation and provenance tracking, offering a depth of semantic understanding that traditional databases cannot support. What is the issue then? Creating knowledge graphs from documents is a slow and manual process that requires expertise in ontologies and also semantic technologies. Most domain experts have data, but not the tools or specific knowledge to annotate them. If we have an expert in conservation or archaeology, they are expert in their field, but they don't know how to translate their data into a representation with the right ontologies and the right structure that a machine can understand. So this is where artificial intelligence jumps in to help us. Recent advances in artificial intelligence, particularly in NLP or natural language processing and computer vision, allow machines to analyze, understand, and work with data such as text and images that are trivial to understand for humans, but not as such for machines. These systems can identify entities, detect relationships, and extract relevant information, effectively assisting in the transformation of unstructured data to structured data and structured knowledge. Natural language processing, in particular, or NLP, is a subfield of artificial intelligence that focuses on enabling machines to understand, interpret, create, and work with natural language. This includes very different tasks, such as identifying key entities in a text, for example, people, places, and objects, as I mentioned before, recognizing the relationships between these elements, and extracting meaningful information from unstructured text, such as reports, scientific analysis, description, or historical documents. In the context of cultural heritage, this is especially important because a large portion of the available knowledge is stored in textual form, often in different languages and with varying levels of structure. More recently, large language models, or LLMs, have significantly advanced these capabilities. These advanced models are trained on a very large collection of tests and learn statistical patterns in language, which allows them to understand the context, disambiguate the meaning, so understanding also the semantic part of the words, which are for machines just number in origin, and generate or extract information in a more flexible way compared to traditional ancient methods. Unlike earlier rule-based trained system, large language models can generalize across different domains and different types of texts, making them particularly useful when dealing with heterogeneous and complex databases, such as those found in cultural heritage. In parallel, computer vision enables machine to analyze and interpret visual data. So 3D representation or scans or pictures or drawings and images. It allows the identification of the objects, architectural elements, textures, patterns, which can then be linked to the semantic concepts. For example, recognizing a column, a material, or a structural feature in an image. A key concept that supports both language and vision models is that of embeddings. Embeddings are numerical representation of data, whether it be words, images, or objects, in a shared vector space, where similar items are positioned closer to each other. This allows the machine to capture aspects of the meaning and the similarity. For example, relating different description of the same monument that we can find in different data and different PDFs or linking a textual reference to a visual representation. So this document is talking about this monument that we have an image of. In our case, this model can support tasks like identifying relevant entities within documents and images, suggesting relationship between them, and helping mapping this information into a structured representation, such as the knowledge graph that we were talking about before. So we thought, what if there was an AI-based assistant that could help you read and understand your data and extract structured knowledge? So we could go from the scientific PDF, for example, and directly have a knowledge graph in a faster, more efficient way. So a scientific PDFs can be made up to 20 pages or more. We can have multiple PDFs about the same object or talking about different aspects of the same object. And to relate them, we need to have the prior knowledge and to read them all manually. And then identifying all the entities and the concepts and the relevant information inside them. With the help of artificial intelligence, we are able to speed up this process and also make it more efficient and reliable. Instead of manually encoding every relationship, we use AI to suggest the structure and let then the experts validate him in an automated approach. The use of open source models guided by the domain ontologies helps in grounding the results and reducing the risk of hallucination, which can be typical of artificial intelligence models. Using open source models, so AI system whose code and parameters are publicly available, also gives us greater transparency and control over the system, which is fundamental when working with things such as cultural heritage assets. It allows us to run the models, the artificial intelligence models, locally, and also adapt them to domain-specific requirements. So why this approach matters? It matters because it makes the work faster. It makes it accessible, so usable by curators and researchers without the need of knowing any particular technical skills such as coding or querying languages for knowledge graphs. And this approach is also successful because it is adaptable. So it is compatible with different domain ontologies, and it is reusable. So it can work across different domains. As an ending plus point, it is also collaborative. So we just don't let the AI decide. We work with the AI. We combine the power with artificial intelligence with essential human expert validation, which is of course still needed. So inside the Artemis project, in the data infrastructure team, we noticed a gap in the cultural heritage space and decided to try and create a bridge using the power of artificial intelligence to help experts and work better in order to have an efficient, reusable, and grounded backbone for reactive heritage digital twins. This was a brief overview of how within the Artemis data infrastructure team, we are building the foundation for reactive heritage digital twins, not just static replicas, but dynamic connected system. By combining network science, ontologies, and artificial intelligence, we aim to ground data, make relationships explicit, and enable richer understanding, while moving towards a more scalable, efficient, and reliable process for transforming unstructured data into structured knowledge. Thank you very much.